Back. Alright, so what we're going to look at now is a few more sampling algorithms. Alright, so the problem with rejection sampling is it rejects nearly everything. Turns out we can do a lot better by not rejecting instead of weighting them. So instead of rejecting lots of samples by sampling the observed values and then throwing them out, we're basically not going to sample the observed values, and instead we're just going to weight the samples according to how likely it would be that they would be rejected. That's one instance of what's called importance sampling. So the idea is that samples have weights. It's a real number associated with each sample that takes the evidence into account. So we're going to take the evidence into account, and that's going to weight the samples. And so then the probability of a proposition, the probability of some alpha given the evidence, is looking at all the samples where alpha is true of the weight of that sample divided by the weight of all the samples. So we're going to look at this says summing over all the samples where alpha is true, the weight of the sample. This says we're dividing it by the weight of all of the samples. Okay, and so we're going to mix exact inference with sampling. We don't sample all the variables, but we're going to weight each sample according to the probability of the evidence given the sample. So here is this algorithm. It's called likelihood weighting. It's an instance of importance sampling. There are lots of importance sampling algorithms. This is one of them. And so what we're going to do is use it to approximate the probability of some hypothesis given this evidence E in a belief network, Bn, and we're going to use n samples to do it. And H here has the domain, we're going to assume H has the domain 0, 1. So we're actually going to compute the average value of H, but the average value of a 0, 1 variable is its probability. Okay. So what we're going to do is we're going to something called the mass. So we're going to start with the weight as 1. And each time we're going to add up the probability mass of everything, which is going to be mass, we're going to add the weight to it. So the H mass is the probability mass of the hypothesis, and we're going to add the weight is going to be multiplied by the value of H. Here it's either 0 or 1, but in general it can be anything for it to compute expectations. So that's what we're going to do. We're going to have, so the weights are going to start off, the masses are going to start off as 0, and each point we're going to add it to, after we've found the weight of the sample, we're going to add it to the mass, and we're going to add it to the mass depending on whether H is true or not. We're going to multiply it with the value of H. Okay. So now what we're going to do is, what happens is if it's observed, so we're going to look at each variable xi in order, and if this value is observed, we're going to, instead of sampling x and then testing whether it's OI is true, we're going to work out what's the probability that would be accepted. And that's this. Okay, and that's what we're going to do. We're going to multiply the weight by that. So we're going to update the weight. So for observed variables, instead of sampling them and rejecting or accepting them, we're going to work out what the probability of acceptance would be, and we're just going to multiply it by that. And if it's not observed, we're just going to do a random sample of probability of x given the parents of xi. And again, this is just this one-dimensional sampling that we saw before. So we know how to do that. And in the end, we're just going to divide the probability mass of where H is true divided by the total probability mass. Okay, and it turns out we can use Hoeffding's inequality on this based on the probability mass of everything. All right, so here's what's going to happen. So let's draw out all the samples first. What we're going to do is look at sample S1 in here, and we're not only going to so now we're looking at the probability of tampering given their smoke and report. So we're going to sample tampering, but we're not going to sample smoke and report. We're only going to sample the other variables. Named here fire, tampering, fire, alarm, and leaving. Okay, so that's what we're going to do in here. We're going to sample all of those. So we're not going to sample smoke and report because they are observed. We're going to sample all of the others. We're going to do it in order again, in order of which we've done it, because now we always have the parents. We can always sample from the distribution given the parents. So let's look at this first weight. Well, it's got fire as false, right? But we know that smoke is true. So what we're going to weight it by is the probability of smoke is true, given fire is false. It's going to multiply by 0.01. So out of all samples like this, only 1% would survive. Leaving here is also false. So we're going to do the probability of report given not leaving, so it's 0.01 again. So it's a very low weight. Okay, by the evidence. Let's look at the other ones in here. So now here's all of them. So now we have the other case of fire is true. Okay, but for fire is true, we can do the probability of smoke given this. It only depends on fire is true. And we're going to do the fire is true, it's going to be weighted by 0.9. Here leaving is false, so it's going to be 0.1. Here fire is true, so we're going to get 0.9. But leaving is true. So the probability of report given leaving is 0.75, which is why we get this 0.75. Again, this has the same, although this has different values for tampering, this has the same values for fire, which is joined to smoke, and leaving, which is joined to report. So it has the same weight. And we're going to do all of these things again. So this is how much it would be rejected if it was using rejection sampling. But instead of doing that, we're going to weight it. All right. Oh, we're going to do that. All right. So one of the things we can do is that what we did before, although it was sort of looked like the probability, we actually did the average value. We did the expected value. So the expected value of some function f of worlds with respect to a distribution f is, so you're going to sum over all the worlds, the probability of world of f, the f value of the world times the probability of the world. That's just the expected value. Okay. I'm going to do something so what we're going to do is we're going to sample this. We're going to do lots of samples, trying to sample according to this probability distribution. And we're going to do the f of s. And 1 over n is the number of samples we're doing here. Notice there's no conditioning here, so this important sampling, this adding in observations is a way to actually do this. So this is a probability distribution, was a conditional before. Conditioned on observations, but it doesn't really matter. As far as we're concerned here, we're going to consider that. Okay, and with our n samples. So that's what we did. We computed this expectation before of h. So now what we're going to do is we're going to do something very strange. We're going to divide by q and multiply by q. That's the only thing we've done here. So all we've done here, we've just swapped it around. We've divided by q and multiplied by q. And divided by q and multiplied by q is, of course, 1, as long as q isn't 0. Okay, so we haven't done anything here. But what this let us do is now we can treat this as our new f. We can sample this, but according to the distribution of q. So we can do it as we're sampling this, but we're selecting it according to the distribution q. It turns out this is a huge advantage if we can select the q distribution appropriately. This distribution q is called a proposal distribution, and all it requires is that if p of c is bigger than 0, then q of c is bigger than 0. Nothing, you just solve that easily by making q of c always bigger than 0. And what we try to do is to try to design, so remember what happened here was that this was bad when these probabilities ended up being close to 0. And so what we'd like to do is we'd like to make the weights end up far from 0. So it turns out proposal distributions are really nice things to do in here. All right. So here's another algorithm. It's called particle filtering. So here's a review of what we did as important sampling. For each particle, right, what we did is for each variable, we did the sample, we sampled the value for the variable, we absorbed the variable, we absorbed the evidence, and then we updated whatever it was that we were interested in getting the probability of. So we can view it in this way. For each particle, for each sample, we call them particles here. For each particle and then for each variable, particle and samples, you can think of the same thing. So for each of these samples or particles, we're going to loop through all the variables, and then we're going to sample the value of the variable. We're going to absorb any evidence there is, and we're going to update the query. And if you know how programming works, then you notice that these two for each variables can be swapped around. You get the same answer. So instead we could do for each variable, then we're going to go through each particle, and we're going to sample, absorb the evidence, and update the query. All right. So you might think, well, what's the point of doing that? Well, there's two ways of doing this. There's one of which is we're going to have a new operation which is resampling. So we're going to regenerate samples. And it also works because we can have infinitely many variables. When we have a hidden Markov model, we can do this. So we can have it sample for each variable. We're going to look at each. We're going to then loop through this, and it essentially goes on forever. So we're just looking at all the particles. We have lots of particles that we're going to all maintain at once. We're going to sample each one, we're going to absorb evidence, and we're going to update a query. So it's different. So here's the algorithm for hidden Markov models. So we're going to start with a randomly chosen particle, say 1,000. And each particle, in some sense, represents a history of observations. And initially, we're going to sample the states in proportion to their probability in the initial state. So that's the initial one. So we're going to sample each one according to how likely it is according to the probability of S0, probably initial state. And then we're going to repeat this. We've got lots of samples. We're going to absorb the evidence. We're going to weight each particle by the probability evidence given the state of the particles. So that's essentially what we did last time. We updated these weights. But now we're going to do something a bit different. We're going to resample them. We're going to select each particle at random in proportion to the weight of the particle. And some of these particles are duplicated and some may be removed. And all the new particles have the same weight. So this is similar to what we did in, if you remember what we were doing, we did stochastic local search. We were viewing these methods that had lots of different particles. We're doing something very similar here. And then we're going to transition to the next state for each particle according to the transition probabilities. Okay. And then to answer query, to do filtering about the current state, we use the set of particles as our data. We're going to estimate them for those from that. So we're going to estimate, again, probabilities from data. So here's an example that we did before a long time ago, if you remember, on localization. So we have the location of the agent is down here, and it depends on the action of this. And now I can have multiple sensors. Here I'm assuming we're having k sensors at time 0 and k sensors at time 1 and k sensors at time 2, etc. And we're going to assume here, for the example I'm going to give, is the location consists of an x, y, and theta. And we can actually have very dense representations of x. So x and y can be sort of very accurate, maybe to the nearest centimetre of where this robot is. And theta can be the angle, maybe to the nearest degree of where the orientation of the robot is. Okay, so it can have the location and the orientation is now the location. So it's not just a finite set of, well, it is a finite set of points. There's no real number here. It's just a lot. There's just a lot of states. We don't want to view this in the way before, because once you have a big domain, we can make x, y, and theta to be quite fine, but we're not going to discretize it. We're not going to reason about each state. We're just going to reason about some particles. And here in the example we're going to look at, there are going to be 24 sonar sensors in the example we're going to look at, all very noisy. So here is a domain of where we have, so this is a domain about where we have, here's the robot is here, so each of this robot is here in this green dot, and the orientation is given by that little arrow there. There are 24 sensors around here, and they're trying to detect walls. Notice how they're very noisy. So this one here goes all the way through this wall and thinks that there's a wall here. This one here thinks there's a wall here. These two are sort of accurate. These two here at the bottom here are right here are reasonably accurate. This is pretty good here. This goes away into the wall. So these are pretty noisy sensors. It turns out having lots of noisy sensors is okay, and because we only has to be sort of as accurate as a number of hypotheses. Now each of these red dots is one of the samples. So what we're going to do is to basically uniformly guess. Say, here's one hypothesis. So each of these is a hypothesis about is one of the particles, and it contains an xy position, and they also have an orientation associated with it. So each of these particles is this. So essentially there's just a few thousand hypotheses about where the robot can be. Okay, so that's what's going on. There's a few thousand hypotheses about where the robot can be. And we'll just show this for a little time, and after a little while we end up down here, and the robot's moved down here and is facing that direction. And what happens is that the resampling leaves particles where we think it's going to be likely. It's very unlikely that the particle is in here based on our observations so far, right? The robot sort of was up here and moved down to here, and sort of the particles are now no longer uniformly distributed, but they're where it could be based on the very, very noisy sensing information. It could be. So each of these particles now, the resampling is now going to allow us to, the resampling is going to, put us near where hypotheses that actually fit the evidence. And if we move through here forward and we have a few more moving positions, then we'll find that at this point here, these points in here are the most likely points given the history of sensing. It's very unlikely the robot is down here. There's a few particles through here, but it's very unlikely. It's very unlikely it's here. It could be up here. It's very unlikely to be over here. There are no particles over here. They've all been rejected, so we keep resampling. But these represent the probability distribution about where the robot can be, right? It's probably, it's quite likely here, but it's also quite likely over here where there are other red dots. Okay, so that's what's going on here. So we keep resampling, lets us concentrate our hypotheses about where we think it could be. Okay, and so basically we're thinking about this is lots of hypotheses that are tracking it. So we're going to talk a bit more about this in class. Thank you.